started. So last class, we introduced this notion of what's called a vector field. So I don't want red. I think this is lecture 39. Who the heck knows? What a fiasco. I do know it's the 17th of April. So last class, so we defined vector fields. What do they look like? They're functions that look like something like this. F, it might have two inputs. And then we can even have one that takes on 3 and spits out 3. The idea is that the input of the function is either 2 or 3 variables, and then the output is either 2 or 3, either a vector of either 2 or 3 dimensions. That's kind of how you want to think about these things. Now, we tried to give you a little sort of peek in how we might think about them and some physical examples. I don't pretend for a second that that what we talked about on Wednesday is all that easy to understand. It could have in many ways been more confusing. I don't know. But what I'd like you to do is just try to pick one of those examples that we talked about, whether it's wind on the surface of the earth, or it's trying to understand how fluids might move. Think of those, or maybe a magnetic field or a gravitational field. You can think of those as realistic things in the real world that we might want to model using a vector field. And why are vector fields useful? Because to every point in space, they assign a vector. And that vector is great because it can illustrate to us a direction and also maybe a velocity or a direction and a force. So, you know, again, you got to find something that for you and every one of us is different, that it makes sense. What I just wrote on this board is just two vector fields. There's nothing remotely special about them other I just made them up in my head right now. So we tried to give you some realistic examples last class. Okay, now we're on to some fun stuff. So today's a big day in many ways because we're at what I consider one of my favorite topics, at least getting into them. And why do I like this? Because this is just, for me, this is like real, so much of what you learn in calculus almost seems redundant. Not redundant, that's a pretty bad way of saying it because it's really important, but you spend so much time just doing these procedures. Let's integrate, let's integrate, let's integrate. And then you're like, holy hell, the machine can do it. Why am I spending so much time doing it? And then let's take derivatives, let's take derivatives. And we see these sort of procedures we repeat over and over again. And this is not much different now, but to me, it's so much more interesting because it's really, you're now in the precipice, it's a bad way of saying it. You're now, well, there's a couple of funny things we could say about this, but we're now really starting to learn things that help us solve, real physical problems. Most of the examples we did in Calc 1 and even in Calc 2 are just what we would call toy examples or textbook examples. Hey, let's minimize and maximize, right? Well, yeah, those have there's use to that, but a lot of that is just created because we want to give you, hey, here's a very baby example of the real world. When they're not very realistic in that sense. But here we're really there. So we're now sort of, funny enough, this math is still a couple hundred years old, but it's important in many areas. So today we want to talk about what we call line integrals. And this name is very misleading for a few reasons. And we'll explain that in a second. So here's what we've integrated over. We've integrated over an interval. This was Calc 1. Then we decided we're going to integrate over an unbounded interval. This was Calc 2. We did this. Then in Calc 3, we learned we can integrate over a region in the plane. That was Calc 3. And then we talked about we can integrate, and this is going to be hard for me to sort of draw, but think about this as, that's bad. Let me just draw something that's easier to draw. Then we talked about integrating over solids in 3 dimensions. So this was a region in space. That was Calc 3. So if you want the symbolic stuff, this was the integral from a to b of f of x for both of these. And then down here, we introduced the double integral. And down here, we had the triple integral. Now, all these types of integrals had their use. They were something we can define as some arbitrary mathematical object. But they also had many uses. For example, we found that they can do geometric things like areas and volumes. We found that they can do other things a little more sophisticated, like centers of mass and work done. So there's lots of uses for these things. And now we want to talk about integrating over a more general object, a curve. So we now want to integrate over a curve. So here we go. So to motivate it, let's sort of think of a geometric representation. The way I sort of have always asked students to think about this, and we're going to show you, there's some really great graphics on Wikipedia of this. The way I would want you to think about this is if you've ever had a bathroom with a shower in it, and some people have like a glass or a plastic sliding shower door, but other people have like a shower curtain where you have something that protects the water from coming out. And so you imagine this shower curtain hangs, and sometimes, you know, for aesthetic purposes, it's actually longer than it should be. And so people bunch it up and it like hangs and it has like a curvy bottom. Or maybe another way of thinking about this is if you have curtains in your house over a window, and how the curtains might hang and how the bottom of it is sort of like a curved thing. And what I'd like you to do is I'd like you to think about is that is like, well, I'm going to show you a picture in a second, but keep that visual in mind. So bear with me for a second. Hopefully right now you see Wikipedia. And where is the picture I want? I want the picture. I don't want the vector field. Here we go. So can you guys see what I'm showing you right here? Everybody see this video, I hope? GIF, whatever. So you have a curve in the plane, and you want to ask, what does the function look like above that curve? And this visual gives you an idea. So what we'd like to do is look at this particular piece. This is your hanging curtain. So here's your domain. And then now we're going to look at, we evaluate F. And when we evaluate F, we have a curve in the domain. And now we look about what happens to this curve. Imagine you're running along a road that goes up and down, just like this. And we might want to ask, like, what is your distance traveled? What was your elevation change? And one of the ways we can do that is through this type of integral. So let me try to make this as clear as possible, although I'm not suggesting that it's easy. So let's imagine let's take, say, z equals f of xy on some domain D. So we're taking an input of two variables. And so we know the graph. Got all kinds of stuff here. So we can interpret the graph as a surface. In space. You know, for example, we have our old friend z equals, say, 1 minus x squared minus y squared. This is our paraboloid. We've graphed this numerous times. Well, we haven't done it recently, actually. So we might remember this thing looks like this. So it sort of looks like this upside down bullet. Best drawn in GeoGebra. Now, what we would like to do is we would like to imagine a curve in the domain. So what does a curve look like? Well, oh my God, what is happening to this? So if I consider a curve in the domain, what does my curve look like? Well, my curve, you guys will remember, has this kind of form. Let's call it C. So here's what you need to remember. What is a curve? A curve is really, the way we think about it is it's the range of some parametrized or a function R like this. So we'll call it C. What does C do? It's some curve. So if we have our domain, what does our curve look like? Well, our curve is just some trajectory. So, you know, this could be, say, R of A, and this would be the point R of B. Now, instead of integrating over all of D, we only want to integrate over that curve. So instead of considering f of xy on all of D, just restrict to C. Does anybody have a question or a comment? So again, imagine that D is sitting somewhere in the plane, that's the domain. And what we know is if we plug any point in D into the function, it has an output and there's a surface above it. But we're not interested in that surface per se, we're only interested in that part of the surface that comes from plugging points in the curve into the function. So if I restrict my function to just that red curve C, what I'm essentially going to get, if I want to interpret that way, is I'm going to get a curtain hanging from the surface, just like the curtains hang above your windows or the shower curtain. Now, if you go to the internet and Google line integrals, you get some very useful images that I can't really draw as well. Here's one of my favorites. Let me show it to you here. So right now, I want you, I think you can see this. Is this? This is the picture. Oh my God. No, I don't want to join. Get out of here. This picture that I'm putting my mouse around, this is your hanging curtain. Now, of course, it has different heights because I'm only evaluating the function on that particular curve. So what we'd like to know is, what is the geometry of this hanging curtain? And how can we quantify it in different ways? And then what use is it to us as scientists? The mathematician might say, I have no use other than I'm curious. But the physicist might say, I have uses. Or the engineer might say, I have uses. Or the biologist might say, I have uses. The economist might have a use. So what we'd like to do is say, okay, what is the area of this hanging blue curtain? And how can we compute it? Well, the strategy is very much the same as how we've done integrals in the past. We build a Riemann sum. Okay, so what's the standard procedure? Well, what we do is we start by breaking. Now, the fancy word for this is partition. The domain of R into n pieces. So let's say the domain is AB. Well, then you might have your, what is T? Well, you have A equals T0, and then you have T1, and then you have T2, and then you have all the way up to T sub n, which of course we're going to call B. Let me be very clear what I'm saying, using this. So let's be very sort of clear how we do this. Let's draw some pictures. Remind you how a curve R works. You have some interval T, and it starts at A and it goes to B. And what R does is R takes that interval and it maps it to some curve in the XY axis. So maybe that curve looks like this. So maybe this point right here is R evaluated at B, and this point right here is R evaluated at A. And so out here somewhere in La La Land, let's pick this point. We have some, this could be, R evaluated at some arbitrary point. Let's call it, T sub K. Does that make sense? Now, to be very clear, what is this? Well, this is X evaluated at T sub K, whatever that number is going to be, comma, Y evaluated at T sub K, whatever that number is going to be. Does anybody have a question? So let's draw another piece. Let's draw, for the sake of argument, some other guy. Who comes after k in the number? Well, if k is 6, who's next? 7. If k is 32, who's next? 33. So in general, who comes after k? Who comes after k is k plus 1. Excuse me. Woo! Okay, so what do these do? What do these t's do? So here's the next page. The nt sub k's allow us to break C into n pieces. So let's draw the picture again. This time I'm just going to draw the curve without the coordinate axes. So my curve looked something like this. I don't know. It doesn't really matter. So it starts here and it ends over here. So let's be very clear. Let's give these pieces a name. For lack of a better name, we'll call these pieces C1, C2, all the way out to C sub n. So here's C sub 1, and then here's C sub 2. Out here, this is your C sub k, and then this last piece would be C sub n. Now, what you don't forget, even when we go back to like Calc 1, we want you to imagine that n is a very large number. And that means that these little curve segments are very, very, very small. So of course we can approximate them with straight lines if we wanted to. We've done that in the past. Let's do the following. Denote their lengths by ds sub 1, ds sub 2, ds sub 3, all the way up to, why am I using s? That's just a standard convention that we use. And you'll see why in a second. Does anybody have a question? Okay, so let's build and we're following the same exact theme as we followed since Calc 1. You chop up the domain you want to integrate it on. We chopped it up on these little C's of these little curved C's. And then we evaluate the function at some arbitrary point inside. So next, evaluate f at an arbitrary point on each C sub k. So what would that look like? Well, let's be very clear. That would look something like f evaluated at r of some point t. So how we did that in the past is we did this. We used this asterisk. You could go all the way back to Calc 1. We use this asterisk. Where is t sub k? T sub k star is any point less than t sub k plus 1. Well, I guess I should, yeah, that's fine. I mean, I can do it that way. I guess perhaps the better way of writing this, though, is to not use it that way. I guess I'll do it this way. Let's use t sub k here, and then it has to be bigger than t sub k minus 1. So t sub k star is just, it's in that interval somewhere. So perhaps, for example, this point right here, this is the point r evaluated at t sub k star. Does that make sense? Okay, so here we go. Fun times at calculus. We can now make a definition that has some physical intuition, albeit it's hard for us at this level of our life to get the physical intuition for it. I don't know why. So what this does is this suggests the following definition. The integral over a curve of some function. Now we're going to write ds here. Well, why would we not write dx? Well, dx makes no sense to us here. What are we integrating over? We're integrating over a curve. So we're going to use s because we don't want to write x. That would be misleading. And how would we define this? Well, we're going to define it with this crazy limit. Excuse me. So we're going to explain what these symbols mean in 1 second, and we're not going to ever deal with this sum again, but this is the definition. So this is called the line integral of f over c. So here, delta equals the maximum of delta S1, delta S2. So we take the longest one of these guys. And what else we have to do is we have to assume the limit exists for all partitions. So you pick any way you want to chop up AB, do this, and if the limit exists over all of them, we say it's integrable. Now, we're not going to be looking at this sum ever again. I just wanted to do this once to help. I shouldn't say you're not ever again. You might, maybe. What I'd like you to do, though, is I would like you to try to think about this construction. Think about how this limit and this thing on the right, this sum, is somehow related to those pictures I showed you of that, you know, on the internet. If you just Google line integrals and go to images, you know, you'll see that. And think about how that works. Now, the question is, as you guys know, if we're going to be computing these things, how do we do that? How does that definition, how does it relate to a formula for computing these things? I mean, you guys clearly know that we're not going to be able to use that definition. That's ridiculous. Okay, so enough scary stuff. Let's tell you how to evaluate it. So here's the intuition. So we're integrating over a curve. So we would like to know, you would imagine the length of that curve is going to have some influence on what this integral should be, right? If we're integrating over a curve, the length of that curve is going to matter. So recall, the length of C is what? Well, the length of C, we're going to give a name. This is sort of how we would like you to think about what's happening. So the length of C in general is what? Let's call it S, because that's the standard variable we use. The length of C is the integral from A to B. You'll remember this formula. It's the length of the derivative of R prime of, say, whatever variable you want. Let's say y dy. That was our arc length formula. We studied arc length way back in Calc 2. We studied it again a few months ago. It's given by that, the length of that. That is the arc length formula. So thus, if t is between a and b, we can define s of t as this integral. The upper bound has to be. So this up here, this is the varying bound. Now, here we go. Now we're going to use some, again, this is intuition. This is not specific. This is all true, but to show you why it's logically sound, you don't do that in Calc 3. You go to what we call advanced calculus courses. All right, now we're going to use the fundamental theorem of calculus. What does the FTC say? It tells us how to differentiate this. So by the FTC, it says ds dt is just equal to the length of r prime evaluated at t That's what the fundamental theorem of calculus says. You go way back to Calc 1. And then we go back to some more useful way of writing this. So in differential notation, we write ds as this. So what does this mean? What do we expect? Well, we expect, excuse me, the line integral over c of f ds to be equal to the integral from a to b of f evaluated at r times ds. But what's ds? We just told you what ds is. ds is r prime of t dt. Don't forget, this is what we just alluded to. This creature right here is d of s. So this is how we compute line integrals. Now, there's nothing special about using a curve in the plane. I could have used a curve in space, and the necessary adjustments would be made. So what I want you to pay attention to before we end, and then we're going to do a bunch of examples of these, don't worry, is the line integral. Notice that you're starting to see now why, integrals have the notation that they do. The ds, this differential, that is telling you sort of what are we integrating over. In Calc 1, when you did dx, you're integrating over the x-axis, or you're integrating over I guess you could think of it as an interval or a line. Then when you go to double integrals, we're integrating dA, we're integrating over a region in space. Or triple integrals, dV, a region in the plane. Then triple integrals is dV, where we're integrating over a region in space. So we thought of dA as the area element. We thought of dV as the volume element. And what we want you to think about ds, we want you to think about that as the element of what's the size we're dealing with. Well, we're integrating over a curve. So we want to think of ds as sort of like the element, the length of a little piece of a curve, the infinitesimal piece of a curve. And if you draw a picture, this r prime of t dt, this ds is not going to surprise you, because that is nothing more than the tangent line, right? The tangent line to a curve is r prime of t. If I take the absolute value of that, I am getting its length. So all this is suggesting is that we're approximating a piece of a small curve with a straight line. And you guys in Calc 3 have to start to be aware of the fact that taking any curve, if you pick a small piece of that curve and zoom in on it enough, it becomes a straight line. It begins to resemble a straight line. I mean, that is the whole idea behind how television and monitors work and how movies work. I mean, how does a monitor work? How do graphics work? These pixels. So there's some really interesting things lying deep in behind this. So you have two options. Your option is one, just to learn how to integrate. Don't give a damn what you're really doing, and that's fine. The other is to really try to think about what all these symbols mean and the deeper meaning behind all this. It's quite fascinating. It's not easy to do that. It takes a lot of suffering, but if you get to that point, sometimes it's, I don't know, it could be rewarding, I think. I forget, did I post the homework yet? No, I didn't. So I'll have to do that today. And we'll give you some practice with this stuff. Does anybody have a question? Let's do one of these real quick before we leave. And then we'll move on. So let's integrate this. So we have to give you a function. Let's say where f of xy is 3x squared plus y squared. And C is the parabola r of t equals t squared on 0, 1. So there's a few ways you can proceed. A great tool to visualize all this is to go to GeoGebra and look at this. I'll try to maybe make an applet where you can do that. Make it a little easier to visualize. So here's what we know. We know that this, by definition, is the integral. Where are we integrating? We're integrating from 0 to 1. We're integrating f, and we're evaluating at r of t. And then we're taking the length of the derivative of t dt. So now we have to plug in what these things mean. And this is, again, this is usually, I'm going to give you some practice on even doing this, because it's something that when you're in my position, you forget how strange it is. So what is f? Well, f is 3x squared. So this becomes 3t squared plus y, which is t squared squared. And then we're multiplying that. So I'll put it in brackets. What is the length of r prime of t? Well, that's going to be the length of, what's the derivative of r? The derivative of r is 1 comma 2t dt. So this is usually the step that you either get this part or you don't. Does anybody have a question about this? This point. So I am composing f with r, and that's how I got the thing in the brackets. And then I took the derivative of r, which is 1 comma 2t. And now I have to do the arithmetic. Yikes. So let's go one step at a time. This equals integral from 0 to 1. We have 3t squared plus t to the 4th. And now I have to take the length of 1 squared plus 2t squared dt. Which I'll clean up first. Which looks like this. So does anybody have a question before we finish this thing up? Now, I'm not going to do this integral because it's very challenging, but, and that's not the point right now, that you can have a calculator get this part done for you. This could be done using some trig subs. So if any of you are up for a challenge, go integrate it and see if you get the same answer as, say, Wolfram. Does anybody have a question about this? By the way, I pointed this out to you guys in Calculus 2, that line integrals, arc length integrals are typically very challenging to compute. Well, since the arc length thing pops up in line integrals, you would expect that most of these are very challenging. Fortunately, we're going to have lots of shortcuts and tricks, but we're out of time to talk about that today. Does anybody have a question? All right, listen, guys, have a great weekend. I apologize for going over. I didn't realize that. Sorry. I'm going to stop recording now.